Now, this is our node-level parallel programming course. In the previous courses, we've seen how to use the cluster and had an overview over the hardware. Now we want to go into more details and to see how to how the hardware and the CPU works in details and how to optimize applications on the cluster. So we will have a little overview over what we've already talked about in the previous course. And we start with the hierarchy of the compute cluster. The most coarse-grained view on the cluster is if you stand in front of the cluster and you see it in the white space. So this is how it looks like. And then we can take a closer look at one of the racks. So if you open a door of the rack, then you will see the rack. And it has multiple compute nodes or blades in it. And in this case, this blade has 3 compute nodes. And one node here is comprised from 2 CPU sockets and some networking hardware and also the cooling. So we have here the 2 CPU sockets and the RAM, that the main memory that belongs to the CPU socket. And then we see here the CPU's chip, and we see that it actually has multiple chips on this CPU package here. And in the middle is the I/O die, which takes care of talking to the memory and the others, CPU socket and the I/O, the networking hardware, and maybe the GPU and other devices. And we have these little ones that contain the cache and the CPU cores. So as we see here, it is divided. There's a hierarchy here in these NUMA nodes. We will later today talk in more detail about NUMA. So 2 of these dies belong to one NUMA domain here, and also some of the RAM. And we have 4 of them per socket, so 8 of them in total per node. Then we can go further into one of the CPU chips, the dice here, and we see that they have 4 cores and the level 3 cache, which is then shared between the cores on one of the CPU dice. And then we can go further and take a look at one of the CPU cores, and then we have the L2 and L1 cache and the execution units and some control logic. So this is basically in a nutshell the hierarchy of the compute cluster from the compute cluster up to one CPU core. So this is just some things that we already also talked about in the previous course, and what I've already mentioned, the 2 sockets that are connected and the main memory. We have 8 channels per socket here, and we have our CPU socket here with the CPU dies, the I/O die that connects the CPU cores. Therefore, if there is a memory request coming from the CPU core, it goes through to the I/O die and then goes to the main memory through this memory controller. So everything goes here through the I/O die. And we have this architecture here with the 2 CPU sockets that are connected. And actually, it's a symmetric multiprocessing system. This means every code that runs on one core can access all of the resources on the complete system. So it can access all the data on this, on the memory connected here on the other socket. So it has to go through this socket interconnect. And it could also talk to the devices that are connected here through the I/O ports of the other socket. So you can every core can access all of the resources. And then we have our cache hierarchy. This means that if we have our CPU cores here, our little processors, then we have our memory on the bottom that is connected via the memory interface of the CPU. So if there's a memory request going from the CPU core, it has to go through this cache hierarchy because there's a long way from core to memory. Therefore, the cache hierarchy makes sure that often used data is cached, and therefore the access to the cache is much faster than access to the memory. Therefore, we have some cache levels here that cache the data. And we see, if we take a look at the sizes of the caches, the level 1 cache is most closest to the core, is the smallest but also the fastest. So the latency is only up to 8 cycles. Then level 2 is 12 cycles, but it's larger with 512 kibibyte per core. And then we have the L3 cache that has 4 megabyte per core, but the latency is 46 cycles. And then the memory interface. So if your request goes to the memory interface, then it's quite slow. And the L3 cache is then shared between the cores, but the L1 and L2 cache are private to each core. So here again we see the chip and we see the structure here with the 8 cores and the L3 cache in the middle. Now what we want to do in this section is we want to go even deeper and take a look how does a CPU actually perform the computations, because depending on this, you can also optimize your code to make it more suitable for the CPU architecture. So you can get a better performance. For this, you have to know how it actually works. And because we're also going to take a look at measuring things in the CPU to get to know the behavior of the CPU when it runs your code. So we're gonna take a look at what happens if we actually run instructions on a CPU. Now, if you have some C code, for example, here you have some value in memory. So this is no global memory, but it doesn't really matter in this case. And you have a function. The function is just incrementing the value of this variable. Then you have to translate it into the machine code. And if you translate it and then execute the program, then this machine code is stored in memory, and then these instructions are executed by the CPU. So here we see our memory hierarchy, and on the right side we see our CPU, and the CPU is actually a CPU pipeline. This means it has multiple steps, and the instructions has to go through these steps. And we see here two registers, so little spaces, variables inside of the CPU core. So the PC, the program counter, tells the CPU which instruction is next. And the R1 is just a register here that we can use for computations. Now we can go through what happens when we actually execute this code. So the first thing is our program counter is at address 0. This is where our first instruction is stored. And in this fetch step, our CPU has to fetch this instruction from memory because it's stored in memory. Therefore, there's a memory request going to the memory. And then it fetches some data from memory and stores it in this instruction cache. And we see here the addresses correspond to our program binary. So the instruction was fetched, and now it's inside of our CPU core. And the next step is the decode step. Therefore, the CPU has to understand what kind of instruction is it and what are the arguments. So we see here it's a load instruction because the first thing to execute this line is to load this C data stored in the C variable. Therefore, it has here some static address that it knows where the variable is stored. And the idea is to load this data from this address into our R1 register. Therefore, the CPU core knows it's a load instruction, and we can go over to the execute phase. And here there could be multiple instructions happening here. In this case, it's a load instruction. Therefore, the execution is to have another memory request at the address that was given by this parameter. Therefore, we have to load some data from the memory into our data cache here. And then the last step is the commit. Therefore, we now have our data, but we still have to finalize our instruction. And the instruction says, get the data from this address and store it in the R1 register. And this is what we're going to do, or the CPU core is going to do, is committing this data into the register. So the registers are the little variables inside of the CPU core that it can use for like scratch space. And then the program counter is automatically incremented to the next place. So the next in this little model CPU, so this is not real CPU architectures, and instruction sets are more complicated. Here we simply have, I'm assuming that one instruction is encoded in 4 bytes. So the next address is 4, and this is why the program counter simply went to 4. And then in this case, it does the next, it fetches the next instruction, and here it's already in the L1 instruction cache, so it's much faster to get this data. It's decoded, it's an add instruction, and here we say C plus 1. Therefore, the thing that we have in our R1 register plus the 1 immediate value that it's encoded here inside of our instruction. And the execution is then quite easy. Just take the R1 register, add a 1, so 5 becomes 6. And then we commit it, and it is stored again into the R1 register, because we say R1 plus 1, and the destination is the R1 register again. Then the program counter increases again, and then we get the next instruction decoded. It's a store instruction. Here we say, take the value from the R1 register and store it at this address. And this is what's going to happen in the store execution phase. Therefore, we get the data, and then we store it in our L1 data cache. Therefore, now we have this value 6 in our data cache. And later, if this cache is flushed, so if there's something, a new data comes in and replaces this this data value, then it will be actually written to the memory. Or if there's some other event that forces a synchronization here. Now this is, as you see here, we have a pipeline of steps in our CPU, and instruction after instruction, it goes through this pipeline to be executed by the CPU core. So this is the most basic concept of a CPU pipeline. We have multiple steps. Each instruction goes through this pipeline through each step. And in this case, it also happens sequentially. And we can think of it as an instruction that goes through through this pipeline. And we have here our fetch, decode steps. We have a queue of instructions, and then a little schedule step here. So this is a little bit more complicated in this case. because we have in this diagram multiple execution units, so for the load, store, and the arithmetic unit here. And then we have our little commit step. We have a register set, and then we have here the access to the memory hierarchy with the caches. So this is our CPU pipeline, and we're going to take a look at how modern processors work to increase the performance of the CPU pipeline. And we see here our pipeline stages. Therefore, we assume that each step takes one cycle. Therefore, in the first cycle, the add instruction is in the front end here, in the fetch decode queue. Here decode in the queue, and then it goes through these cycles here when going through the pipeline. And now if we have two instructions, we see that when the add instruction goes in the second cycle into the next stage, then already the store instruction can be in the fetch stage. Therefore, they go sequentially after each other through these stages. And this is the idea of pipelining. Therefore, in the pipeline, the instructions can go through the stages, and every instruction takes only up one stage. Therefore, other instructions can take up the other stages at the same time, as we see here in our stages here. However, our store instruction, there is a dependency because the store instruction needs the data from the add instruction to be executed, because the store instruction wants to write the result from the add instruction to main memory. Therefore, if it goes here through, then the green bubble here has to wait until the add instruction is finished, is committed, because there's a dependency. It needs the result of the add instruction to be executed. Therefore, it has to wait in the schedule stage. Therefore, it has here a red place in the in our diagram here, in our table of the cycles. It has to wait for the add instruction, and once the add instruction was in the commit phase, therefore wrote the value back to the register, then the store instruction can be actually executed and then take the result value and write it back to memory. Therefore, we see here we have a dependency, and the pipeline has to stall. This means the other instruction also can get further. Therefore, there's a little congestion here at the schedule stage, and the other resources here are not used while the pipeline stalls, while it has to wait for the instructions to be executed. And here we see 3 add instructions, and we see that if we make the execution units also into pipelines, then we can have multiple add instructions inside of our ALU here in our execution unit. Therefore, they would not stall yet the schedule, but we can actually have them inside our 3 stages of our add execution here. And this also increases the performance because then, well, we assumed that one add instruction would only take one cycle, but there are other instructions, for example, the division instruction, which takes a lot of cycles usually because it's more complicated. And then it would stall the pipeline for longer time. Therefore, if we split up this execution into multiple stages, then we can also already fit multiple instructions into this execution unit. And here is another example for this kind of thing. It's floating point multiplication. And floating point numbers are more complex than simple integers. They have a structure here. We have a sign bit, we have an exponent bits here, and we have the mantissa here. So they have a format and the specification, the IEEE 754 specification that is implemented in the hardware. And if we want to pipeline and split up the multiplication of floating point numbers, then we can create multiple steps, sub-steps of this. For example, separate the mantissa and exponent from the number, multiply the mantissas, add the exponents, normalize the results, and insert the sign, and then create the number again in the specified format according to specification. Therefore, when before we had one execution of the instruction would take a lot of cycles and could only hold one instruction. If we create a pipeline out of this execution out of this instruction, then we can see that the first value that we want to multiply goes through this pipeline of floating point multiplication. And then if we have the next value, then it can go already in the first stage, while the first multiplication is already in the second stage. Therefore, we have a sub-pipeline for this floating point multiplication that increases then the performance of our execution. So this is also a part of modern CPU architectures. And the next thing is out-of-order executions. And here the CPU can track the dependencies of the instructions, and it can check if the instruction or a different instruction that comes next could already be executed even if the instruction that comes before inside of our actual program wasn't finished yet. And in this case, we have a loop, and we just add a constant to some values in an array. And if our program loops in our CPU, it will basically do a load and add in the store multiple times over multiple iterations. And as we see here, all of these instructions or the iterations are independent of each other. Therefore, they are interchangeable. Therefore, this load and this load could happen in parallel if they wouldn't use the same register. So if we load the first value in this register and then we load the second value in this register, then it would overwrite the first value. But the CPU is, or the designers are smart, and they created a system to check the real dependencies, because this add depends on the value that was loaded before, and this add depends on this first load. And they know that these registers that are specified here in these instructions, they are like placeholders, and they can be actually replaced. Therefore, the CPU can track the add has a dependency on this value that was loaded here, and this add has a dependency on the load that happens here. Therefore, the CPU knows that it could actually run these loads in parallel and already load the next value while this add is still running. And the store of this value is happening because they are actually independent, even if you use the same registers. In this way, this CPU can already start with the next iteration, even if the first iteration isn't finished yet. And if we can think about if this wouldn't be an add but a division takes a lot of time, multiple cycles, then if this wouldn't happen, then this second iteration would have to stall for a very long time and waiting for the first division, and this way this load can already happen, because the CPU knows that this load doesn't have to wait for this division. It only has to figure out which instructions are depending on which values that were loaded before. So the CPU has a lot of shadow registers and then maps the real values to the instructions that actually depend on them, even if we have only a limited number of registers that we can use in our instruction expression. Mm. Now, another optimization in modern CPUs is branch prediction. And here, if we have some code that has a branch is a jump in the program code. So there are conditional branches and no, there are conditional jumps and unconditional jumps. So an unconditional jump is if we have some instructions, something should happen in our code, and then we jump to a different place in the program code. Therefore, the program counter has to change, but it's independent of what happened before. Therefore, the CPU already knows, okay, I can just get the next instruction from this jump target and then continue with our instruction stream that are in memory, stored in memory. But with the conditional branch, it's not so easy because here, as in this case, the next instructions, so that belong to code path 1 or code path 2, that should be executed depend on the result of our condition. So this condition has to be evaluated. This is some instructions have to be executed in our CPU. For example, there's a comparison of some values, and then depending on the result of this comparison, we continue with the instructions at this place in memory or at this place. Therefore, if we think about our instruction stream coming here, and the comparison is going into the execution units, the CPU pipeline has to stall because the CPU can't know what is the result. And branch prediction is a system where the CPU takes a guess. So it guesses, maybe this time it's code path 1. And then it's already executing the instructions that come from code path 1, or that if we follow this jump here, and then already starts to execute these instructions, even if the comparison has not happened yet. But in this case, the results of these instructions are not committed. Therefore, the CPU waits until it actually has evaluated this comparison, and then it knows, was my guess correct or not? This way, the CPU does not have to stall and can already continue executing some instructions, even if it doesn't know was my guess correct or not. Now, the problem is if it was not correct, it has to throw away all our work and continue with the other code path because the guess was wrong. But if it was right, then we actually saved some time because we already executed the correct instruction and we guessed correctly. And to improve the guess, there is some systems. For example, the CPU can cache the place of the comparison instruction and then track, okay, the last 50 times I did this comparison, it took always the code path 1. I assume it will also take the next time the code path 1. For example, if you have a loop that's iterating over an array, then we will always jump back to our instructions in our loop. And only in the last iteration, after the last iteration, when we do the comparison in our loop, then it will jump out of the loop and continue with other instructions. Therefore, it would always do the loop and only in the end it will jump out. So our guessing would always be do the loop and only at the end it would be wrong. So this case, in this way, the CPU can avoid pipeline stalls. This is also a little bit a waste of energy because we're actually doing some work here and executing some instructions. But for the best performance, one could say it's worthwhile, and therefore in high performance CPUs it's implemented. Another optimization technique is widening the CPU pipeline. Therefore, we can't fetch one instruction at a time, but we could fetch already the next few instructions and store them in a little cache here in the CPU. And one can also add a decode cache here and have multiple instructions that go through this wider CPU pipeline. But this also means that we have to adjust our bandwidth here through our caches and the memory hierarchy, because if we make the CPU pipeline wider, so it can work on more values and instructions at the same time, then, and if we would not improve our memory hierarchy, it would always wait for the memory. So we also have to make sure that the CPU pipeline can be fed with data from our memory system. And it's also an investment because then we have to invest more logic and so on our CPU. But then we can also do something called simultaneous multi-threading. And in this case, we can run multiple programs at the same time. And with program, I mean threads. So threads are like instruction streams, and these threads don't even have to belong to the same process. They can be different processes. But then we also have to ensure that everywhere where there's something stored that belongs to a thread, for example, the registers or the cache values, there we have to track if this data belongs to the one thread or to the other thread, because this is also a security issue. One thread shouldn't be allowed to access the data of another thread. It could belong to a different process. For example, one process is your browser, the other process is your password manager. There's a conflict there, a security conflict. Therefore, the CPU has to track which data belongs to what thread. And then we can make use of the resources. For example, if one thread has to do a lot of divisions and is stalling here, then the instructions of a different thread could be executed when they are doing some memory operations, and then we can make better use of the of our CPU execution units and our CPU resources. Yeah. So on HPC systems, this is disabled on compute nodes because we assume that HPC programs are actually well optimized and they make good use of the CPU resources here. Therefore, if you would activate it, then the threads would actually compete for the resources of the CPU, and then it wouldn't help, basically. But it's very good for example, notebooks. If you have some in the foreground running application, they have some background services, and then the background service can do a little bit work on the same core as the foreground thread. And then it's more efficient. Another very important optimization is single instruction, multiple data. So before we've seen we have one instruction, for example, an add instruction, and it will be doing the work on one scalar data value. But what we can also do is we can add some new instructions, and these new instructions take vectors of data and then operate on the elements of the vector. So before we had our registers with only one value, and now we have our vector registers. Then we can load a vector register from memory, and we also have to extend our register set here to accommodate all of this data inside of our CPU core. And then we can store, for example, 2 vectors of elements, and then with one instruction, a vadd instruction, compute all the addition on all of the elements, and then we can store the result. And for this again, and these additions can be done in parallel. For this, we have to also extend our execution units to actually be able to run that many additions in parallel. And we have to extend our memory, because if we now have super instructions that load multiple values from memory, then we also don't want to wait for the memory, because then we would have invested a lot of resources to make our CPU core more performant. It could execute a lot of additions at the same time, but then we have to wait until the data is trickling in from the memory. This also then would be a bad investment. So we also have to extend our memory access here. Now, what are the reasons for suboptimal pipeline performance? So as we have seen, our CPU, we just have a pipeline that is fed with instructions from our memory. It always needs more instructions, more instructions. I want to execute some instructions. Then they go through this pipeline and get some data in and data out. But then we have these stalls. And in stalls are basically wasted time, because if we wouldn't have a stall, if we wouldn't have to wait for the memory system, or we wouldn't have to have so many divisions, then in this time we could actually execute some other instructions. And there can be, if a stall happens, and so let's think about the perfect case. The perfect case is in every cycle, in every stage, there is an instruction. Therefore, the pipeline is complete full. There's no stall. It always runs through. Everything is busy. Therefore, we get the best performance that we could have with our CPU pipeline. And if this is not the case, this means that in one cycle, somewhere in our CPU pipeline, a stage was not busy. And these places in these situations are then also called bubbles, because they are bubbling through the CPU pipeline. For example, if we have a problem in our fetch stage, we have to wait for the next instructions because our memory system is busy. Then in one cycle, there was not an instruction loaded. And then in the next cycle, it can also not be passed to the next stage. Therefore, this bubble, this not executed work in the fetch stage is then passed to the code stage, because it is not fed by the fetch stage. Therefore, this bubble trickles down through our CPU pipeline. And if this happens at the front end here, then it goes through the complete CPU pipeline, but it also could happen in the other stages. For example, the schedule stage, if we have a lot of divisions, then maybe the CPU pipeline has to stall here, and then these bubbles are created here because we have to wait until there are some free execution units. Therefore, a happy CPU pipeline is complete full, and a sad CPU pipeline is full of holes, because then we can't use the resources of our CPU. And one way to think about optimizing a program is to think about why was the CPU pipeline set, at which point was it overloaded, and then change your program to compensate for that. Now, one important thing are memory accesses. And here, I've already talked about this cache hierarchy. When we can think a little bit about it, then what we want to do is we want to do some calculations. This is the main reason that we have the CPUs in the first place, but we need the data for it. Therefore, we also have to make sure that the CPU pipeline can be fetched with data from the memory. And as explained, if we take a look at the performance of our memory accesses, because this is crucial for calculating things, we have to get the data fast enough. If we access our level 1 cache, this happens in 4 to 8 cycles. If our memory request can't be finished by the level 1 cache, then it has to go to the level 2 cache. So we look for the data in the level 2 cache. Then we already have to wait 12 cycles. And if it's also not there, then we have to go, the memory request has to go to the L3 cache. And this is already here 46 cycles. And if it's even not there, if it's something that was not previously stored in the cache or was flushed because the cache was full, then we have to go to the main memory, and then it's a real yeah, a long time, because the memory request has to go out of the chip. So here we are still on our CPU die, on the core die, these little ones with the core and the cache. But now this has to go out of the chip. It has to be has to go a long way between the core die and the I/O die, and then from the I/O die even again out of the chip to the memory, and the memory is stored on this other one. So there are some electrical connections here, and this takes a very long time. Here we don't count in cycles anymore, so CPU core cycles, but we count in nanoseconds. So this is a real long time. And in this time, basically the instruction is stalling the CPU. If there are no other instructions that can be executed at the same time with out of order execution and so on. But we need this value for our calculation, and the CPU has to wait. Therefore, if we can make better use of our cache hierarchy, then we can also don't have to wait and can better utilize our CPU. Now, one technique to improve this is to do cache prefetching. So the idea here is that we have some load, and then we have to have some cache misses. This introduces latency, and before we can do the work with our data that we wanted to load, we have to wait. And if it's loaded, it's loading multiple values. Therefore, our next load instructions can be answered by the caches. Therefore, this is faster. We have less latency. We can already do the work until the next load that then results in a cache miss, and we again also have latency. For example, in a loop where we go over an array, we get some data the first time, again until the block that we at the end of the block that we got in this first memory request here, because there are always blocks of data are loaded when we are doing a memory request. They're loaded into the cache. Now the idea of cache prefetching is we have a system where we already loading some data that we are not needing immediately, but we know that we will need them in a short time. So in this case, we already prefetch the data of the array because we know we need them. Then the load instructions are executed, and they don't have to wait because the data is already prefetched in the cache, and also for the next iterations, for the next requests. And there are basically two ways to realize this. And one is a hardware prefetch. Therefore, it's already included in the CPU. The CPU notices, okay, the program is kind of iterating linearly over the memory. It could be something like a loop that goes through an array. Then I will already get the data that comes next, because apparently it's needed when the loop will reach this place in the array. So it can already load some data into the cache. And then it has some pattern detection inside of the CPU and see, okay, not even if it's going linearly, but if there's some stride, so this is also linearly, but we have some jumps, or maybe some more complicated pattern. And the other, so this is then included, and you usually can't turn it off. It's just part of the CPU architecture. And the other way are software prefetches. And here, these are included special instructions inside the program that are added by your compiler if it detects, okay, this there could be a performance improvement if I'm adding this prefetch instructions inside of the program code that instruct the CPU to already load some data, even if the real work is done a little bit later. Now we've seen these general techniques. They're implemented by the basically the modern CPUs of multiple vendors. But in our case of Nocta 2, we have an AMD Zen 3 architecture in our CPU cores. And here you see the more complicated structure and schema of this Zen 3 pipeline. We have our fetch here, we have this branch prediction, we have an operation queue, this decoding stage here, then we have a dispatch, we have this split into an integer and floating point unit here, and then we have a scheduler, and then we have this row of execution units, and then the instructions have to go through here and then dispatched, and it's all a lot more complicated. And to assess the performance, we can take a look at what's happening in the actual CPU pipeline, because the vendors also add ways to gather some performance metrics while the CPU is running. So we can take a look what is happening, and from this we can then take a conclusion how to optimize a program. And so we first have to think about what performance metrics do we need. So wall time is the most easiest one. We look at the clock, run our program, and look again at the clock. Then we take the difference, and we know how long it took. We can take a look at the number of executed instructions. Therefore, there's a counter in the CPU. It just counts the instructions, and we can read it out. Then we know how many instructions were executed. We can look at the past cycles. So a cycle is depends on the CPU clock. Therefore, the CPU frequency, the clock frequency. Therefore, we can see start of the program, end of the program, how many cycles were passed. But then we also think about that the frequency can change depending on the load of the CPU. So there to save some energy. So we have to think about what does this number mean in the end. And then we can also have an average instructions per cycle, how many instructions were executed in how many total cycles. And we have the CPU frequency, and we can take a look at the actually executed operations, how many operations were executed. And here we count in floating point operations. We can differentiate between double precision and single precision. And we can think about scalar values and vectorized values. And we can take a look at the memory requests, how much data was pushed through the memory hierarchy, and what is the cache miss rate in percent. And these are metrics that one can look at and then see if, for example, if we have a very low memory access data rate, we load only few data values and then work a lot on these data values, then this is a different behavior of a program than if it needs a lot of memory, and then maybe we need to think about different ways to improve then the performance of this program, because then there's a different bottleneck in our program. We can think about the theoretical peak performance of the of our CPU, and therefore we can we look at the specification of the CPU, and we see if we have a certain frequency that we assume, and then we can issue 2 instructions per cycle. So in each cycle, the fetch stage can be fed with 2 instructions in the ideal case. And then we have our instructions that are executed. Therefore, if all the instructions are vector instructions, because then we have more operations per instruction. In this case, we can have 4 elements per vector, and we assume double precision, because then 4 double precision values fit in one vector. And which instructions do we want to execute? In this case, this is the fuse, multiply, and add, because then we can have 1 instruction but 2 operations. We have a multiply and an add operation, then we could say, okay, these are 2 operations. And therefore, this would be, if the pipeline is always filled, therefore per cycle, we have the maximum number of instructions that can be executed or operations done by the CPU pipeline, and then we can get the peak number of operations per second. So we multiply all of these things, how many cycles in a second do we have, how many operations can we do, and then we see that we can have 38 gigaflops on per second on one core. This is the theoretical peak of the CPU core. And if we look at the turbo clock, if you're only using one core, then we could calculate 56 gigaflops. Now this is the theoretical peak, and you will only achieve this if your program is basically just these types of instructions. And if all the memory requests are perfect and the pipeline is always full, and this case usually never happens because in a normal program you have a lot of other types of instructions. Maybe you have some divisions that take a long time, and in this time you can't do other instructions. You have control flow instructions if you have to jump around that slow down your CPU. Maybe you have a not ideal memory requests. Then you will not reach this peak, but it's still useful to think about it because it gives a natural limit in on your CPU, and you can think about and measure what is my current performance and what is the peak performance and what is the way to improve the performance of the program to come closer to this peak performance of the CPU architecture. And here we see multiple architectures, and then you could compare these peak performances and see that they are all of the factors contribute and are very important for this peak performance.